Hi everyone, welcome back to this special edition of Comp 3430 Operating Systems, and welcome also to my messy office. Yesterday's lecture kind of got cut with the audio. Sorry about that. This is an effort to try and fill in that gap of what our discussion on signals was. So let's get started. We figured out before that processes cannot communicate through variables. So once you fork a process, a parent and a child process can't communicate through variables anymore. If we make changes to one process's variables, it doesn't have any effect. It doesn't have any effect on the child process. But we still need to be able to communicate, to share data, or to coordinate work. And we were able to use pipes to send data between two processes. So that was giving us the ability to send information between two processes, but we still want to be able to use another IPC mechanism called signals. So signals are a primitive communication mechanism, and they're primitive compared to pipes in that all we're really able to say is that some event has happened. And here are some examples of the kinds of events that you might imagine using signals for in a program. First is it's okay to access a shared resource now. So when you have multiple processes trying to do things at the same time and they're operating on the same shared resource, so like a file, for example, a signal is a mechanism that you can use to coordinate between processes. It's your turn to work on the file now. The shared resource in reality here is something like a road. So the walk symbol or the do not walk symbol says, as a pedestrian, it's okay for you to use this shared resource that is the road. The red light and the green light tell cars, it's your turn to use this shared resource that is the road. Another way that you can use signals is everybody should start now. So here's the starting pistol. As soon as you fire it, everybody starts at the same time. This is a synchronization approach. So I want to make sure that nobody starts early. I want to make sure that everybody starts at the same time. I want to make sure that all processes start working on something at the same time. The other contrived example is to indicate that something is ready. So on mailboxes, on really old mailboxes, there's this flag that the mail carrier will flip up to say, hey, you got mail, so that you don't have to go out to your mailbox and constantly check, hey, is there mail now? Hey, is there mail now? Hey, is there mail now? This is something that a signal is something that you can use to send that flag to a process. Hey, I put data into this file. It's now something that you should start working on. We're going to take a look at the mechanical use of the Signals API. And the way that you do that is first, in a process, you register a signal handler using the signal system call. You do other stuff. So your process is now free to do whatever it wants to do. And then eventually some other process is going to send signals to that process, either using the kill program or using the kill system call. Our goals with the example that we're going to take a look at is to send signals with the kill program and to send signals with the kill system call. I want to see what happens when a signal is received by a process. So once it's started running, I want to see what happens when a signal is received. And I want to figure out which signals we can't handle and then be able to explain why we can't handle those system calls. So let's take a look at some code. Here is the code sample that we were taking a look at in class. One thing that might be new to you is this approach to setting up a structure. So using this :2 syntax, this is what's called a bit field. And a bit field is a way for us to say that even though this is an unsigned int, it should only have 2 bits. And because it only has 2 bits, it can only ever have 4 values. So because this is 2 bits, it's either 0, 1, 2, or 3, 0, 0, 0, 1, 1, 0, 1, 1. And we're using this feature to kind of make sure that we can just forever increment this. So count plus plus here, we can forever increment it And it's always just going to loop back around. It's an unsigned integer. So when it's 0, it's 0, 1, 2, 3, 0, 1, 2, 3. So it kind of like makes this little spinner here. This program basically just prints out its process ID. It writes to standard output what the spinner is, and then just goes to sleep for 1 second. So let's take a look at registering a signal handler for this process. I'm going to start by taking a look at the manual page for signal. The manual page looks a little bit different here because I'm running this on a Mac right now, but it's ultimately the same as the one that you see on a Linux system. So the first thing that we have to do is include signal.h. So I'm going to go back up to the top here. I've already got that included. And the other thing that this is telling us is we have to have something that's called a signal handler. This is the signal handler prototype or signature that we have to have. So it's a function pointer, and it's a function that has a void return type. So void here, and it takes an integer as an argument. And then the way that we register that signal is by calling the signal system call, specifying the signal number that we want to register this for, and then the function pointer that we want to run when that signal is received. So let's start this out. I'm going to say void handle signal, and I'm going to say int sig, so to represent the signal number that we're receiving. And inside this signal handler, I'm going to printf received signal %d, and I'm going to pass to printf the sig, so the value that was actually passed to us. Inside my program now, I'm going to register the signal handler. So I'm going to say signal, and I want to register the signal handler for a specific signal. We can check out which signals are available to us by using man7 signal. This is section 7 of the signal of the manual pages. On Linux, this is section 7 of the manual pages, but on Mac OS, it's actually present here in the main manual page for signal. So we can see some of the different signals that we are able to handle. The one that I'm going to be handling is sig user 1 and sig user 2. So I'm going to say sig user 1 here, and what I want my process to handle is handle signal. So what this says is when this signal is received, I want to run this function handle signal. Let's try to compile this program. So I'm going to change directory into my example here. I'm going to make this program, and I'm going to run it. So this prints out the process ID, and then it just sits here and it's spinning. So it's in this infinite loop waiting forever. The first thing I'm going to do is send a signal with the kill program. So I'm going to say here kill, and then kill takes a couple of arguments. The first argument that it takes is the process ID that you want to send the signal to. So 3604 in this case. No, that's wrong. It takes the signal that you want to send first. So I'm going to say kill-user1. So this is just like cutting off that sig part. And then it takes the process ID, so 3604. I'm going to hit enter on my keyboard. And I want you to watch what's going on down here when I hit enter on my keyboard. So as soon as we do that, what happens is whatever this process was doing is suspended. So the instruction pointer is kind of like spinning around in this loop. Line 28, line 29, line 30, back up to line 28, 29, 30. And you know, these write system calls are compiling down to many instructions, but we're going to just pretend that this is an instruction pointer for now. Whatever it was doing here is suspended when the signal is received. So it's kind of like a context switch between processes, but it's happening within the same process. And we immediately start executing what's in our signal handler. So in this case, all we're doing is printing out printf received signal, whatever, and then we go back to where we were before. We continue executing. So it's kind of like taking that context switch off. We're popping off the state that we did, and we're returning back to wherever the instruction pointer was in the execution of the program. This is how we register a signal handler within a process. The other thing that we want to do is send signals between processes. And I'm going to do this in kind of a silly way. As opposed to sending signals between processes, I'm going to have this process send a signal to itself. I really just want us to see the mechanical use of this API right now. So to send a signal between processes using the signal and kill system call. So I'm going to say man kill. This is going to take me to the program that is kill. I want to go to man2 kill. This is the kill system call. We have to include signal.h, which we've done already, and kill takes 2 arguments, the process ID and the signal that you want to send. So I'm going to say kill this process's ID, so mypid. I got the process ID up here on line 21, mypid, and then I want to send SIG_user1 to this process. So I'm going to quit my manual page here. I'm going to make my example again. Make. I'm going to run signal again. And it kind of like immediately prints out that it's received this signal. And that's great. That's kind of all we expected to see here. The last things that we want to be able to do with this is figure out which signals we can't handle and explain why we can't handle them. So there's one signal that we send to processes pretty commonly, and that signal is Control-C. Control-C is sending the interrupt signal to a process. I'm going to comment out this line to send a signal to myself. And what I'm going to try and do here is register a signal handler for sig interrupt, for the interrupt signal. So signal, sig int, and handle signal. An unexpected thing that we can do with the program is that we can register a signal handler for the interrupt signal, which is Control-C. And I'm going to hit Control-C on my keyboard right now. And now it's just printing out that it's received a signal because it has. It's received the signal that says interrupt. I need to be able to kill this program still. I need to be able to terminate this program. And there is a way for me to still terminate this program. I'm going to say kill-kill. And I want to send the process ID there. So 4115. So this is forcing that process to quit. I'm going to try do the same thing here, but with sig_kill. If I can override sig_int, then maybe I can also override sig_kill's behavior. So I'm going to make this, and I'm going to run it. And I'm going to try doing Control-C. That's still not going to work. I'm going to also now try doing kill-kill 4223. And even though I've registered a signal handler for sig_kill, I'm not allowed to have a signal handler. I can't replace that default behavior. Why not? We kind of have to have a way to kill a process. We have to have a way to terminate a process. There must be some mechanism for us to be able to terminate a process. Otherwise, we can have processes that can just do kind of like whatever they want. You know, you accidentally, so me, I'm a novice programmer and I accidentally register a signal handler for sig_kill, and then I enter an infinite loop, and then there's no way for me to terminate my program. I have to be able to terminate it. The other is for like more nefarious reasons. So somebody manages to get onto your system that's not you and is able to start running a process that's doing stuff like mining Bitcoin or something. You want to be able to terminate that process if it's doing something that it shouldn't be. It shouldn't be able to just take up all the CPU that's on your system and not allow you to get control back. All right, so that's it. That's the mechanical use of the Signals API. That is the mechanical use of the program called kill and then the system call called kill. And that's explaining why we can't handle system calls. Sorry, that's explaining why we can't handle signals like sigkill. I hope that you all have a great weekend, and I will see you on Monday. Bye.